Hi, everybody. Welcome to the second meeting of the SIG. We have an interesting program today. Riva will talk about the MLIR legalization framework, which is a very important and interesting part of MLIR. Meanwhile, there are two bullets on the agenda doc behind them. If you have any questions, open topics, please either add them here or type in the chat. And also, if you have any updates about what you've been doing, we'd like to hear from the community, please sign up and let us know. So I think it's all yours. Let me stop presenting.
Yeah. This one's way.
It's good. You can see it.
Okay, so I'm going to be talking about operation legalization and MLIR. Legalization can be swapped for conversion or lowering or whatever word you want to use from turning one thing into another. So basically just going to go over some background and motivation, followed by the infrastructure and then questions at the end. So as an initial question is, what do we mean by legalization in this context? This is basically taking a set of illegal operations and converting them into a set of legal ones based on some target description. So an example legalization framework that exists is selection DAG and LLVM. This basically converts LLVM intermediate representation into the machine representation with another representation in the middle of that. So selection DAG will convert or lower the LLVM IR into the machine IR, legalize types, split operations, however you want to transform the high-level operations into the lower level based on some machine description that you give it. And illegal in this sense is basically unsupported. So from the LLVM perspective, let's say if your target doesn't support adds of 64-bit integers, so you might have to split that into two 32-bit adds during legalization or something like that. So some background of existing tool chains and their, lowering graph. So you have Java bytecode, you have Clang AST, you have Swift, you have Julia. They all kind of lower to different IRs progressively, and each IR does some domain-specific optimizations. But in the terms of legalization, every arrow that you see here is converting from one representation to another. And if we go even further, you can take other, TensorFlow graph has lowerings to XLA HLO. It converts to TF Lite, which XLA can go to LLVM IR. So the important thing to notice on this part is that each arrow represents a lowering, but also it represents a completely independent piece of infrastructure that had to be built for the specific purpose of converting from one thing to another. So in one sense, you can think of all of these arrows as completely duplicated work that developers have had to do over time. So when we move into MLIR, we can represent many different abstractions with dialects, and each of these dialects can convert between each other. They may want to lower to multiple dialects. So each of these can represent some partial abstraction level. So you see, for example, the affine dialect may lower to a combination of what is now the standard dialect or a more general loop dialect. So in MLIR, we represent all the abstractions in the same infrastructure, but we still have this situation of lowering between one thing to a different thing, or one thing to a set of different things now. And then because MLIR can represent all of these things, it's much easier for external. It's much easier for external infrastructures to plug into this. So TensorFlow, TensorFlow Lite, XLA, they can all be represented, but they also still need to be converted between these. They want to interplay with the different abstractions that people are building, both in the core repository and outside of that. So it kind of brings us to what we want out of a conversion infrastructure. I've seen a few examples in the previous slides, and this slide pretty much details a bit of a wish list, I should say. It's kind of in the context of MLIR with dialect mentioning, but the problem domain still exists. So we want to support this transitive conversion, and this exists today in other infrastructures. So for example, LLVM IR, Clang can lower to LLVM, which LLVM can lower to, say, x86 CPU. Swift can lower to SIL, which lowers to LLVM, which can lower to an x86 CPU. So we're reusing the same conversions, but on that scale, it's not as nice to interplay with, and it's a bit more convoluted because it's completely different infrastructures. But in MLIR, kind of want the same, I guess, ability. So we want to say if we have some targets A, B, and C, or dialects, we want to transitively convert from A to C if a lowering exists from A to B and then from B to C. At this point, we shouldn't have to define a lowering from A to C. We should get it transitively from what already exists. And this kind of answers the question of what conversion should I define? So even in the previous example, there's a lot of questions that arise of, okay, do I need to convert directly to LLVM? Do I need to convert from TensorFlow to my representation? Like, what patterns do I actually need to write myself to be able to plug into all of this infrastructure that other people are building?
But it raises other questions, though. Specifically, what is B?
Yeah.
or what is the best B?
So, yeah, Chris brings a point of what is the intermediate that you are lowering from A to C, and given that MLIR allows for people to define different abstraction levels, for example, B could be the affine dialect, it could be the Linnow dialect, it could be whatever you want.
It could be HLO at the graph level. It could be lots of other things as well.
So we want to support this transitive conversion, and we want to keep the things that you're lowering between kind of open-ended, because they could be anything based on the abstraction that you're trying to target, or whatever you're building.
Do you also talk at some point about the fact that A often lowers to like more than one thing?
Yeah.
Okay.
Awesome. That was more of the MLIR context.
Okay.
But so we also want to support partial lowering, intra-dialect lowering, and multi-dialect lowering.
Here's a question.
Oh, what's the question?
So legalization is more than just operation type lowering, i.e. you also want to specify pattern lowering?
So it's a bit confusing what you mean by pattern lowering at that point. So it'll go into it a bit more later on what patterns are in the MLIR context and how they're used for the infrastructure. So maybe that'll answer your question then. For the partial lowering, intra-dialect lowerings, multi-dialect lowerings, because we represent all of this infrastructure and all of these different abstractions, the same infrastructure in MLIR, we want to do a slightly more complicated lowerings. So Chris' example was, I may lower to several different things. So in the original example of the existing infrastructures of Clang, SIL, LLVM, all of those are monolithic closed representations. So lowering from one, say, Clang to LLVM, it either has to represent all of the source. So LLVM has to support transitively everything that Clang can support in some form, or you're losing information. So you may not be able to support certain operations. For example, TF Lite may not be able to support certain TF operations. So the conversion would just fail. And it's much more difficult to intermix than an MLIR, where all operations can transitively coexist in the same module, function, computation arbitrarily.
And this is something that in the Clang example, it would be nice to be able to lower out parallelism constructs as a stage. So like do OpenMP optimizations, for example, and then do other scalar optimizations within that, and then lower them, but then keep everything else and lower those as separate phases.
Yeah, so that it comes into the partial lowering of, I just want to lower some things right now and then keep everything for a later phase, or it may turn into something completely different than what I'm lowering to right now.
Another one. Sorry. Any ideas on generating these lowerings automatically from semantics of the dialects, or to ensure proof correctness of the lowering?
So
this would be really, really interesting. So I don't think anybody in our team is working on this right now, but when you start talking about the operational semantics of these ops, and if you can define those, then you can define the transformations across those.
Yeah, so that kind of goes into how patterns or lowerings are defined. So this is just defining the infrastructure that can utilize all of the craziness that people can come up with defining these transformations. This is the kind of thing that we want to enable with a conversion infrastructure.
I mean, I think there's a lot of really interesting research in the world that has been done on similar things that we can look at pulling in over time or trying to figure out how it makes sense. I think that'd be super interesting.
Yeah. But moving a bit forward, we want to support some, I guess, a bit more convoluted, maybe that's a joke. So selective lowerings. So because we can represent both the source and the destination, even after lowering in several cases, we may want to just selectively lower certain things, like all convolutions whose strides aren't prime, because we're lowering to an accelerator that supports that specifically. And that kind of ties into the last target, the last bullet, which is because we can support all of these different infrastructures in the same, we get a different kind of transitive conversion. So the lowering for one op from A to B to C may be different for another op. So a target may say, the target being C, I support this A op directly, an optimized version. Now there may exist another lowering from A to B and B to C, but I support this one optimally. So please choose this one instead. So given that MLIR can represent all of this, we want to support this kind of skipping infrastructure or skipping representation and just compiling to the most optimal thing possible based on all of the different abstractions available.
Which gets to cost more.
Yes.
Other pieces. But I think this is something that selection DAG historically sort of almost got, but there the granularity was you had to say that something's legal or not. And by that, you could say something very high level is legal, and you could say that all of these things should be supported. And that was kind of an implication that that's fast.
Yeah.
So it's supported and fast, but then you can also say it's illegal and it gets expanded to other things. And selection DAG never had the good way to say like this thing expands multiple different paths with different kinds of constraints. So people had to do custom expansion for that.
So after we've laid out kind of what we want, we can go into what the framework looks like in MLIR. And it's very similar to what legalization is as a concept. So there's two main things that you need to provide to the framework and a third optional one, depending on your use case. But the first is just the conversion target, which is just the formal definition of what is legal for your conversion process. So if I'm lowering to LLVM dialect, I would mark the LLVM dialect as legal for the conversion. I don't have to generally care about what I'm being fed. All I really care about is the target that I'm converting to. And this ties in with the rewrite patterns that are provided. And these patterns are just legalization patterns that transform illegal operations into legal ones. And as we've mentioned before, we want to support transitive conversions. So these patterns don't actually have to directly map from illegal to legal operations. There just has to be some transitive set of patterns in a directed graph that will transform one illegal operation to a set of 0 or more legal operations. And whatever that path may look like is just a set of connected patterns. And those patterns don't have to know anything about each other, and they can just kind of form together as the infrastructure works. So we're talking about a little bit more about that later. But the last optional piece is a type converter, which is the definition of how types are converted to those accepted by the target. So, I have a question.
Are patterns organized as a set of rule sets? And is there a sequence of rules sets to apply?
So the pattern in this sense, and I can show examples of what patterns are, is it's a rule set in a sense. We treat it as a rule set. It takes an operation and generates something or some set of operations, and we can use that to check legality. But the patterns themselves are just a transformation. So converting, or in the original example of the LLVM, not supporting an I64 add. So it may get split into two 32-bit adds. All of the pattern has to do is take the I64 add and generate two 32-bit adds. And the framework can tell the query if the generated 32-bit adds are legal for the infrastructure. So we kind of infer the rule sets from the transformations that you're performing and work that way, so that the patterns don't have to know about the infrastructure in general and can kind of be very directed on the transformation that they're trying to perform. So we want the patterns to be simple, extensible, and cover many different types of use cases. But as we're saying about the type converter, you can have 1-to-0 mappings. So say I'm dropping a token type, and I don't want it to exist anymore on the IR. Or say I'm converting from the standard I32-bit type to the LLVM I32-bit type. So 1-to-1 mapping. Or you can even say, for example, I have this high-level type that when I lower to, say, LLVM, it actually gets expanded to several different types, and that has some specific meaning or mapping. So the type converter kind of guides how all of this works.
So, for example, you have a vector of 4 floats, and you turn into 4 individual floats.
Yes. So it gives you the freedom and flexibility to define however you want to map types to your target and convert them. And yes, a little bit aside, when you have type changes, they have to use a special pattern because the original operation has different types than what you're expecting. So this conversion pattern will provide you with operands that map to your original operation, but with the correct type that you expect. So you can still do matches based on the invariance of the original operation and build what you expect as the result. So going into a little bit more detail on what the conversion target does or how you use it, it's basically a simple mechanism where you set a specific action for an operation or an entire dialect, for example. And there's just a few simple actions that you specify. The first one being legal, which is just every instance of this operation is legal. Any combination of attributes, operands, types, whatever, it's always legal. So LLVM conversions would mark LLVM operations as always legal because they always support those different semantics. Then comes with dynamic legality, which allows for you to define more fine-tuned constraints. So in the context of type conversion, you may say, I support the add operation, but only when its types are 32-bit. So then the 64-bit add would be transitively illegal for your target. It would have to be converted by some pattern that you provided. Then the last one is illegal.
Does this framework support N to 1 or N to M mappings of ops when lowering if the target supports, say, a fused operation? Or does the conversion look at a step op at a time, at a single op at a time?
So, I mean, yes, it does. So, I mean, if you actually look in our repo, we already have an example for this. So, I mean, it's effectively asking, can you pattern match from multiple ops to a higher level op? I mean, so in the one of the examples for fusing a ReLU into a fully connected layer, that's actually exactly one of the things we do.
Also, but there may be a difference between the pattern matching infra and the pattern rewrite infra and the conversion infra. Yeah. The pattern matching infra is a little bit more general.
So currently the conversion infrastructure does not support it, but in MLIR, we generally take a pragmatic approach to adding features, which is if you need a feature, that's when we kind of scope it out and add it.
Yeah.
So I would say the implementation right now doesn't, but there's nothing in the system that prevents the support for that.
Right. So I mean, but there's also several different subsystems that all compose together. So like you can find canonicalization patterns. Canonicalization patterns can take an arbitrary number of nodes input and then produce an arbitrary number of nodes as output. And so if you want to do fusion, canonicalization can use the rewrite patterns to do that, and that works great. I think the conversion approach generally scales better and works better if it is really lowering. Right? So if it's turning one op into n ops, it's possible there's a generalization, but I'm worried that will cause cost models and just complexity and everything to just explode.
The pragmatic approach of seeing an actual use case and then figuring out what system it actually works best in. Because as part of lowering, you're lowering to different abstractions, but then you want to do optimizations on those abstractions. So this conversion infrastructure should not generally be used to combine all of your optimizations in there. That should be left for canonicalization.
I think the higher level idea is that as you're designing a compiler flow in general, you're thinking about what levels of IR or what abstractions do you need to expose. And that's a combination of transitive lowering maybe, but also because you want to do specific transformations on that level of IR. And so it's like you need to be able to represent something in a form so that you can transform and optimize it. And so you're exposing new kinds of things.
And that comes in with the partial lowering aspect, lowering specific operations to an abstraction level.
Yep.
Okay, yes, really quickly, the illegal action is just no instance of this given operation is legal. And this means that if an operation is explicitly marked illegal, it should not exist in the final output for the conversion to be successful. So in the partial lowering case, I may be lowering all of the affine operations away. So I want to assure that those operations are gone in the output, but any other unknown operation is free to exist further. So I mentioned partial lowering, and that kind of ties into the different conversion modes to cover the different use cases. And there are two main ones and then a third one. So the first is partial lowering, which is just convert as many operations as possible to my target, but allow pre-existing operations that were not marked explicitly illegal to fail the conversion. So this allows for operations you don't know about in the function or the module to just continue to exist. So in the affine case, everything else aside from the affine operations can just continue to exist and fit in the system.
And that way affine works with target-specific instructions or LLVM instructions or standard ops or whatever.
Yes.
What happens if some of the conversions are incompatible? This is basically the problem of the person who uses the framework.
What do you mean by incompatible?
Well, say you converted instruction A and it now produces a different type, and you have instruction B which consumes the operand but haven't been converted because it failed the conversion.
So that's part of the framework, and it's up to the user to decide what invariants they want or what they expect from the conversion, and that's why we have different conversion modes, and setting operations is illegal. If you expect conversions not to fail, then you either want a full conversion or you want to mark those as illegal. Because
and illegal means that it will emit an error saying like this node is not supported.
Emit an error and fail out immediately. Is there a question?
Sorry. How much of these are really properties of conversions or properties of the results of conversion?
So I'm going to take a stab at what I think you mean. Please correct me if I'm wrong. But the way that the infrastructure works generally is what the user wants is to write a conversion or write a lowering or something. Say lowering a map mol or splitting an add. And the infrastructure infers meaning from the results of whatever lowering that you wrote. So you don't have to have explicit knowledge of the different modes that it's operating under or have to explicitly massage it.
It's more declarative.
Yeah, right. You want to just write your declarative patterns. I want this transformation to happen. And then users of your patterns or lowerings can decide exactly what the semantics they want for. So this allows for the patterns to fit in many different use cases aside from the original one that you generally had. And it ties into the transitive lowering that was mentioned earlier.
Yeah,
So,
I think the answer to the question is really about transitive lowering, right? Because you need to know the outputs of the conversion. And so you're not saying conversion is legal, you're saying the result of that conversion is legal.
Yeah.
And so if you have a transitive set of lowerings, you actually have to know that by going A to B to C, C is legal. B wasn't, A wasn't, right?
yes.
And so you need both of them.
Conversion target is completely separate from the patterns for the specific purpose, so that you don't embed specific meanings to patterns that would prevent them from being reutilized, if you want, from different infrastructure. So moving on to the full conversion, which is simply everything must be converted or it's a failure. Emit an error if anything fails. This is just to ensure that what you get out is everything that you know about.
I think it's worthwhile considering these things from the perspective of users of a conversion, whereas it sounds like you're thinking of it from a perspective of a writer of a conversion, as a writer of the conversion.
I think what we're trying to do is we're trying to split these along two different axes, because we expect that there will be, when writing a lowering, a conversion, you want to think about just that one small piece of the puzzle, and it often gets reused in multiple different contexts. And so, particularly when you're talking about A to B to C lowering, like you want to be able to say, here's a big bucket of lowerings that can be done. So like I can lower a convolution into a matmul. Like that's a mathematical transformation that should exist in one place ideally, and then that can be used in many different pieces. But then you also have people that are like, you have a specific piece of hardware and you're saying, I need to get as many of these matmuls as I can, scoop up all the patterns in the world that can lower into matmuls and then dump them into a bucket. And then now I get lots of matmuls from lots of inputs and very high level ops.
Yes, it's just difficult initially if you're the person writing the conversion or the lowering, because you have a specific use case in mind. So you just have to make sure that the lowering or conversion itself is actually orthogonal to how you're using it immediately in several cases.
And it doesn't have to be. I mean, you can write one-off conversions, so they're only useful in one case. And so you can write very specific code, and that's cool. But you get more reuse if you generalize it.
Yes. And then the final conversion mode is sort of an analysis mode, which is just, if I were to perform this conversion, what would be the result? So, for example, you can get which operations from the original function or module would have been converted had you applied the patterns and the target. So this could be used for things like device partitioning, where you want to know how many of my operations can actually lower to, say, CPU or GPU, and then you can make educated decisions based on what would happen if you were to perform a lowering. Another question?
Is there an example further down? Otherwise, maybe you can talk us through an example at some point in this presentation.
Yes, there's an example-ish of this later on. And then I can show several other ones. So show an example of this. So this is...
How do you describe custom ops in the source plus target of a conversion and allow them in the conversion? For example, a GPU-specific RNN is arguably a target-specific op, and it might be described as a custom op in the top-level dialect. How do you transform how does the transformation deal with the lowering this custom op as it is lowered into the GPU backend?
Okay. So it kind of depends on who's writing the conversion. So one of the nice things is that because we can intercept the op at any abstraction level that you want, you could capture it, say, if you're compiling for GPU, you could say, I know this TensorFlow op, for example. I have a specific implementation of that. I can match the TensorFlow op specifically. And then the rest of, say, the TensorFlow graph would just compile.
Because, for example, you want to turn into a cuDNN call.
Yes.
So like you have an implementation and it's a call to a function.
Yeah. So this was the last bullet in the what we want from a conversion infrastructure is to say, I support this specific op. Now, it depends on how you intercept it based on what the source that you receive, however they model your custom operation. So however they're modeling that information is how you plug into that. And whatever abstraction level you want to write the conversion for, because everything is in MLIR, you can pick which abstraction you match that at.
Yeah, so I mean, the way I would look at this is, so picking like an LSTM op or something like that, that's just a really high level op. I would love to see the framework include a lowering that says, I will turn this into a bunch of control flow around other more primitive TensorFlow or high level tensor operation kinds of nodes. And so this thing can always be lowered to more primitive ops, and those ops can be lowered, and like, so everybody can run this op. And it's not even a GPU specific op. It's just a high-level abstraction of an LSTM or an RNN. But then, you know, with cuDNN, for example, there may be an implementation of exactly that high-level operation. And so you say, I want to match that. I want to make that legal, and I want to turn, and I just want to leave it in the graph. And sometime later, you say, oh, okay, well, this actually gets to the end, and because it's marked legal, this aggregate op is still there, and then I do whatever I want with the output graph. Another thing you could do is you could say, lower that. Like mark it as lowered, but make it lower into a lower level GPU specific thing, like a call into the TensorFlow stream executor, for example. And so you could do things like that and turn into a more imperative kind of representation, if that's the goal.
Yeah. So it's just described, and I was kind of mentioning earlier, you pick the abstraction level. If it's a high level op, you can let it exist in the IR after the conversion.
Yeah.
You could just have a TensorFlow op with all of the others just kind of intermixed in, and you can pick it up later. Or you could target specifically with a pattern matched at that op, and then set the benefit and the cost model and let that take care of you saying, I support that one directly. I have an optimized version. There is a default conversion, but choose this one instead.
So let me give another example before we move on. So like a concrete example of this conversion framework is the TF-Lite lowering infrastructure, which converts from TensorFlow graphs to the TF-Lite flat buffer. And we have a bunch of hardware folks that have been directly using the TF-Lite flat buffer format as the input to their compiler. Now, the problem with that is that that's one very specific set of ops. And some people making their own chips want to handle some of the TensorFlow ops as at a higher level form. And so what they've been doing is they've been pattern matching on the TF-Lite representation to try to like reconstruct up higher level ops out of the primitives that they get from TF-Lite. With this framework, what you can do instead is you can say, oh, well, what I'm going to do is I will add my own custom ops as my own kernels in whatever form makes sense for my hardware. And I'll define a new lowering from the high level TensorFlow thing I wanted to my custom ops. And so you can effectively extend the flat buffer dialect with your own stuff. And then you can use the existing lowering we have in the framework for lowering to the flat buffer, the TF-Lite flat buffer dialect, as well as all the cool stuff that you want to extend that with. And now you can directly leverage that work without having to reinvest one.
Yeah, that's kind of the goal that we're going for here. As I mentioned in the beginning, because all of these infrastructures right now are closed and monolithic, if a hardware wants to say, I want to support parts of TensorFlow operations as well, they have to redo all of the work that they did for TF-Lite and just completely rewrite all of the conversions. Whereas when you support MLIR input, supporting TensorFlow is maybe an extra line, adding the patterns from TensorFlow to TF-Lite, and then you can add your own for specific TensorFlow operations that you want to support. So there's no difference in input. It's just I add more patterns, and now I support a completely different infrastructure out of the box. That's kind of what we're going for here with all of this.
I think there's a question that I interrupted.
Okay.
You're done with questions.
Okay.
One more question?
Yeah, more questions. Am I getting it right? Are you saying that users will not be able to extend TF by adding their own ops like today, since there won't be a conversion possible unless they add a new backend?
So I mean, I don't know if we want to deep dive into the TensorFlow roadmap here, but TensorFlow does support adding new ops. We're not planning on taking that away. We're investigating various proposals of making it so that you can add an op, potentially with the kernel, but then also add a lowering set of default expansions for hardware that you don't provide a kernel for. So I don't think that we're ready to explain all that quite yet, but we do not want to give up on custom ops.
Yeah.
So that's
If anything, we want to improve the support of custom ops everywhere in the ecosystem.
Yes. Yeah, we don't think that going from 1,500 ops down to 1,400 is going to make the world better. We just have to embrace the madness that researchers will want to do new things and figure out how to make that cause less pain and suffering for everybody.
Okay. Quick example. So this is sort of a little bit of introspective into dialects in MLIR and TF right now and how they interact with each other. But we're going to be looking specifically at a pass that already exists today that lowers from some combination of linalg and affine operations all the way down to LLVM. So we have these different dialects that have conversions to other dialects, but some don't have direct lowerings to LLVM. So we'll have to have some transitive lowering. So we're just going to go over the basic things that we talked about initially for the framework and how these get defined. And the first is just the conversion target, which for lowering to LLVM is pretty simple. It's just the LLVM dialect is legal. And then the built-in function operation is dynamically legal because we only want to support signatures that have LLVM types, for example. We want to make sure the types are converted properly. Then the conversion patterns. So all of the lowerings that were shown in this slide, all of these different edges are written as self-contained passes that implement patterns. So all of these can be tested separately, make sure everything is proper, and then when you actually want to use them, you can compose them however you want. So lowering linalg to LLVM and this combination, for example, is just populating these patterns, affine to standard, this loop dialect to standard, standard to LLVM, and the specific linalg to LLVM operations. And you're just building basically a std vector of transformations that you've already written, or maybe a couple of new ones that you've added for the specific conversion. And then because we're going to LLVM, we have this type converter, which LLVM provides, or the LLVM dialect conversion provides a type converter that converts all of our built-in types with some default lowering. So we're just pretty much defining how the types are converted to LLVM. You try the basic lower, or convert one of our linalg specific types to LLVM. And then after that, you just apply the conversion. However mode that you want, there's a star there. So it could be a partial conversion, it could be full conversion. It's kind of up to the user at that point. So each of these can be defined and implemented separately generally. Conversion target is not specifically tied to the patterns, and the patterns are not specifically tied to the target. They kind of all just compose well, and then you apply whatever conversion realistically you feel like. And then this lowers directly to LLVM, and everything is tested separately.
Does the order in which you populate the patterns matter? How does the framework pick between multiple valid lowerings?
So the order in which you populate patterns has no meaning. It doesn't matter. You can add them however you want in any order that you want. So the way that the framework chooses which pattern is based on sort of simplistic cost modeling on what it wants to do. And the cost model can develop as users have specific use cases, but it's pretty much a combination of the depth of the conversion, or how many patterns we have to apply to get to the target, and the benefit of the patterns being applied. And
Can you talk about what benefit means for people who
okay. So for those that are unfamiliar, when you define a rewrite pattern in MLIR, you can provide this numeric benefit or expected benefit, which is the number. And that benefit ties in with which patterns actually get chosen when you're looking at like canonicalizing an operation or using the conversion framework. So
in selection diag nomenclature, that's the pattern complexity concept. Saying we want to match bigger things wherever we can and turn them, and because they're generally more profitable. And if you have a small thing that you want to to be considered to be more profitable, then you bump up its benefit to say it's actually like a bigger pattern.
Yeah. So this cost model gets you is my pattern has more benefits and it's a more direct lowering. And those are the things that we're kind of targeting right now. And I mean, just like everything else in MLIR, this can change based on need and use cases. So nothing's set in stone. But
And on the other hand, there's a benefit. It is a good thing for us to keep it simple because that makes it more efficient than doing some crazy search of all these patterns to try to find an optimal cover.
Yeah. So that's what we kind of tie in the pattern benefit. So we try to keep the infrastructure simple so that if you want a specific lowering to happen, it can always be, I'm adding a new pattern that just does the other, but with, 1,000 benefit or something.
I have a few more questions. What's your reasoning behind doing this en masse, applying a large number of lowering conversions as a group rather than as a series of distinct passes? I'd be concerned that traceability of this might be challenging if the patterns interact.
So the way that we're building it en masse is that the different conversion patterns kind of interact. So if you do it separately, you don't always get the transitive nature of the lowering. If a certain specific set of patterns rely on chaining together to actually achieve a successful lowering. So the reasoning is largely, if you're splitting up into different passes, there's largely an arbitrary division there, and it creates an arbitrary division or separation in the actual conversion process. So we try to make conversions as simple as possible, and then you convert to abstractions that you actually want to optimize at, instead of adding a new pass for each specific one.
I mean, but we also support dividing between passes if you want to do that. So you can achieve that if you don't need the power.
Right, one more question. This was from Alex. Can the conversion be parallelized? This was, I think, in context of the previous topic.
So it depends on what level that you're converting at, I suppose. So specific operations, it's like the pass manager in MLIR is multi-threaded, but there are certain specific constraints that we rely on to make sure that it is multi-threaded. So, for example, if specific operations refer to values defined somewhere else in the module, you may be updating two use lists at the same time or operating on two operations that are connected. So
you can't implicitly multi-thread that.
Yeah.
You can still explicitly multi-thread within the pass if you choose to.
So for example, you can write a lot of these conversions as function passes. And function passes are implicitly multi-threaded because we know for a fact that it is a closed environment that won't interact with anything else. So yes, but you have to be careful about the level at which you're applying this conversion.
So basically the conversion infrastructure pushes it up a level.
Yes.
So it's whatever is calling the conversion infra that can choose to parallelize.
So another one, most of the time these operations are not commutative. How is it going to be handled? Will the benefits, I don't know what he means by this, but will this benefit the hunches of developers or measurements? Will the benefits based on hunches of developers or measurements?
Do you want to talk about how the recursive expansion works? If you expand A to B to C, and then you go to D, but D fails, but there's a D to E, or do you talk about that?
I haven't talked about that.
Are you planning to?
I mean, I can't. This was supposed to be high level.
Pankaj, really a quick time check. We do have two open topics. So
if you stop here, we can go to the questions. Sorry, the open topics.
We can stop here and then
or move other questions to the mailing list.
Mailing lists, yeah. Any questions can be asked.
Awesome. Thank you very much. That's great.
The last question was, can you show how to declare a multi-operations pattern? But I guess I'm not sure to answer it now or on the.
You can answer that on the
mailing
list to provide links to specific instances.
Yeah, there's a bunch of examples.
Right. I think there are two questions, two topics. So the first one is I expect that there will be JIT support, given that will low-level dialects expose architectural abstractions to help optimize depending on low-level details like NUMA, cache, or TLB sizes.
So what's the question? That sounds like what is the plan there? Or?
Yeah,
Will there be
so.
JIT support?
So we already go through the JIT. I mean the LVM JIT. So
You could use the LVM JIT. Alex is on there.
I mean, is the question perhaps like in this lowering, will we consider the final target to which we're lowering?
oh,
This is a community of it.
not conversion.
I can explain more about the question if you want.
That'd be good.
So imagine there are 2 or 4 sockets on your CPU. Will low-level dialects allow to expose that information during the lowering pass, for example, because it will influence tiling or loop distributions?
I wouldn't say that's being, so again, this is outside the conversion infra that River was just talking about. But yeah, we do have this phase in the compilation flow where you go from having what we call ops and then down to loops. So we call it ops to loops, which is not perfectly correct name, but the idea there is you take something like a map MLIR convolution and you need to turn into CPU code, for example, and that conversion is hard. There's a bunch of stuff going on, including multi-core cache, memory hierarchies, caches, vector hardware, a lot of other things go in there. There's a bunch of different algorithms for that. MLIR doesn't magically solve that in its full generality, but a bunch of folks here are building out the infrastructure to support different pieces of that and solve that for different targets.
Yeah, I think we also need a target description at some point, which we don't really have right now, because information like how many processors do you have, what's the cache size, and so on is useful for ops to low-level instructions conversion passes. But we need to take it from somewhere, and somewhere currently are pass options, and that should change. But if you have concrete ideas about how to design a target model for MLIR, you're very welcome to propose them in the mailing list.
Yeah, I think we'll end up with something like the LLVM target info kinds of classes, but there's a big design space there. I don't know if anybody started thinking about that.
All right, do you want to take the next one? Okay, a key concept in some frameworks is having multiple possible optimization paths in flight, since it may not be possible to select between them. For instance, accurate cost-benefit model is not available. Representing this efficiently can be important to avoid size explosion in the IR. Any thoughts?
So this is saying try like several different points in the parameter space to unroll or tile different ways or other things like that, code gen out, see what you get, and then pick the best option. Is that, I think I saw Steven on here. Is that what you're going for? Or yes. So I don't think we have any infrastructure to do that, but we absolutely need to support that. That's a really common, just like a little bit of inline search kind of during code gen. So separate from the conversion infrastructure, we have the ability to have custom functions now, or custom high-level module-level operations, and so you can represent things as having multiple different variants. And so there's a bunch of tools that MLIR provides, like the multi-thread pass manager, that allows you to say, okay, I'm going to code gen this with one strategy in this context, code gen it again on a different thread and with another strategy, code gen it again with another strategy, and then have another pass that says, okay, well, once I've actually done all that lowering for all the things that are in flight, just pick the best one. And if you have a model for what is best, then you can do that. You can also build within a pass several different options, right? And so many optimization and code gen passes will do a certain amount of analysis up front, kind of what River was mentioning with the device partitioning side of things, where you say, let's find out what I can do, what the options are, and then build a simple cost model in the pass, and then just code gen the one thing that you decide up front is the right thing. And so these different kinds of code gen approaches, I think, are all possible in the framework. And it really depends on the details of the problem being solved. don't know if that answers the question. So he says that can work, but it's unlikely to.
So it says doing it that way can work, but it's likely to result in some combinatorially explosive sites.
Yeah. So I mean, do you want to jump on the video chat? And is there a better way to do this that you're familiar with? What do you think is the right way to go?
Yeah, so sorry, can you hear me?
Yeah, we can hear you.
So basically, in some frameworks, so particularly for a lot of netlist kind of optimizations, you often end up with basically multiple alternatives at different points in the network, and then you want to basically consider the cross product of lots of different possibilities at different points. And so the way that they do that is by, at a very fine level of granularity, allow you to sort of represent, oh, well, you know, this operation might be mapped onto, I can't think of a good example off my head, but it might be mapped onto these two nodes, A and B, or it might be mapped onto C and D instead. And then when you have that, you know, sort of 2 or 3 options at a very small level of granularity, but then you multiply it out over 10,000 locations that you might happen, and at a certain point, you don't know what how things are going to end up mapping onto low-level instructions up front.
Yeah, absolutely.
But so you kind of want to keep those think of it as multiple different lowerings in the IR, but you need to store them efficiently so that later when you get down to the end, then you can say, okay, now I do some pattern matching where I have a relatively accurate cross model of how instructions are going to map onto large groups of these things.
Yeah. So are you asking in the context of the conversion infrastructure that River was
well, I think it's
just in general?
Yeah, I think in general, but I think it's worthwhile thinking about how you do these kinds of lowerings, especially if you're trying to do it across a large range of dialects.
So I think there you have a couple of different options, and again, it really depends on the details. So River, I guess, dodged the actually hard part of this, which is you do this recursive expansion, and you may end up with something that's not legal, or you may end up with 2 different paths. And how do you choose the cost model between 2 different possible paths when you have multiple levels of expansion? And so our answer right now in the conversion infrastructure, just keep it really simple. Keep it very predictable so that us as compiler engineers can understand what's happening. And if you're not getting the right thing, then you can just add more patterns. And so we make it really cheap to add more patterns, and therefore you can nudge the system in different ways by adding patterns. For what you're talking about, I think you want something a little bit more elaborate. And that's where MLIR having the ability to have regions attached to operations, I think, could be very powerful for this, because there you can say, I'm going to scoop out 5 different operations, an arbitrary abstraction level, and I'm going to multi-version it. And so I'm going to have a multi-version op that now has 2 or 3 or 4 or 5 or 10 regions underneath it that represent each of the different versions that you're now evaluating. You capture that in the IR, and you can put inside of each of the regions attached to that multi-version op, the different options that you're considering, and then push all those versions through whatever lowering or other things you want to do, and then sometime later cull. Right, and pick the winner.
Yeah.
So I don't have a lot of experience working on these kinds of use cases, so I don't know how to solve the scalability problem of that. But it seems like if you want to have multiple different options representable, you can then do your lowerings, and you can separate out the transformations from those representations.
Cool, thanks.
All right, I think we're out of
There is
time.
one more question. Is TensorFlow integration a subject for a future meeting or outside the scope of this group?
I think we could talk about it here. I think it's probably more than one hour discussion, but we could have multiple different discussions if people are interested, talking about different aspects.
Yep.
I mean, talking about the TF Lite and that kind of piece, I think could be itself a very interesting discussion.
Talking about the converter? Or?
Yeah, the planning of the converter, the both the the converter formerly known as Toko, but also all the other features and all the other work that's coming. I mean, there's a bunch of different aspects of that, the challenges. There's tons of topics we could talk about. So if you're interested in that, then please, +1 something on the weekly meeting doc, and we can schedule that. We're also really interested in getting community contributions too. So if somebody non-Google wants to talk here, then please let us know. We'd love to see
Any
that.
external users of MLIR should also be definitely encouraged to present what you have or your experiences or how you used it. It's not just stuff that's going on in the core. It's definitely the entire ecosystem of using it.
Yes, and basically, please let us know what topics you want to hear about. If some part of the system, for example, is unclear from the code, we are happy to present. Also, would be great to hear from you guys on what you are doing. Basically, anything that you would like to see on the agenda, just add it to the agenda or send an email to the mailing list and things will happen.
And we see this as an extension of the mailing list as well. So this isn't we don't want all communication to go through this meeting, but we think it's a good way to supplement and grow the community and connect in a different way. So please use the mailing list too, I guess.
I know there are 2 more questions, but I guess we're out of time. So let's take that either on the mailing list or we can address it next time.
Yeah. Sounds good.
All right. Thanks, guys. Thanks, everybody.
Thank you.